Hello and welcome to another worked example with Dr. Schleif. In this question, we're considering a cyclist who is traveling at a constant speed up a hill. It tells us that the frictional force resisting the cyclist's motion is 8.0 newtons. The cyclist uses 450 joules of energy to travel a distance of 20 meters. What is the increase in the gravitational potential energy of the cyclist? And you can see some answer choices down there. All right, let's jump over to the chalkboard. Sometimes students will look at what they're solving, gravitational potential energy, and they'll think, well, there's an equation for that, mgh, right? They try to sort of find the mass. We know that gravity is 9.81 here on Earth. If it's an Earth type problem, you know, what's the height? But this isn't really that type of problem. You know, we're going at a constant speed, so we're not changing our kinetic energy. You know, we're going up a hill, right? So saying like, well, what's going to be the increase in gravitational potential energy? They sort of tell us, somehow we know that it took 450 joules of energy to travel a distance of 20 meters. But there was a resistive force. And so this question is really about calculating how much energy you have to spend, you know, against a resistive force. And then we'll subtract away that energy from the total energy we spent to travel that. And then all the rest of the energy must be our increase in gravitational potential energy, right? So this question is really about understanding that this equation is a dead end, and that there is a more general equation for energy that we work with. Work equals force times displacement. And indeed, we derive that equation for gravitational potential energy by just considering, you know, if we lift something, the force we apply to lift it is its weight, mg. And if we're lifting it vertically, we call that displacement a height. So there's h. And so it really just kind of say, well, that equation there comes from the definition of work. The work that we do lifting an object is equal to the gravitational potential energy that object possesses at the height we lifted it to. But here we just have to sort of say, well, we've done some work, sort of, you know, friction has done some work against the cyclist, 8 newtons over a distance of 20 meters. So we simply calculate that the Newton meters or joules of work that's sort of done by friction, or the work that we're doing against friction, would be 160 joules, which if we subtract that away from the stated 450 joules of total energy it cost us. In other words, we had to spend 160 joules just to sort of fight against those resistive forces, you know, friction, which leaves us with what, 290 joules left over, which must have increased our gravitational potential energy as we went up the hill. Keeping in line with the way that we've been doing these, we'll take a look at our answer choices. Yep, choice B, 290 joules is up there. And if you were to check the mark scheme, you'd find that indeed choice B is the correct answer. This is Dr. Schleif, still living the physics life. We'll see you next time.